Universidad de Zulia en Venezuela, Universidad de Barranca en Perú, Universidad Nacional Mayor de San Marcos en Perú, el CIMESTAP de México, Universidad de Puerto Montt en Chile, Universidad Antofagasta, Católica Antofagasta en Chile, y de todos los miembros de la red LAFMAT. Saludos desde Perú, desde Lima, Perú. El día de hoy tenemos un invitado muy especial, el profesor Stuart Holmes de la Universidad de Cambridge y del University College of London. El profesor Stuart Holmes hizo su PhD en el Imperial College of London y trabajó como investigador nato en Nueva York. Luego retornó a Cambridge y trabajó en el laboratorio de la compañía Toshiba y en el laboratorio Cavendish de la Universidad de Cambridge con el profesor Tony Blanc y el profesor David Ritchie. Desde 2017 es un investigador visitante, profesor visitante en la University College of London. Es un especialista en lo que es fenómeno de transporte, semiconductores, transistores, y es además un buen amigo mío desde hace mucho tiempo en la Universidad de Cambridge. Bien, entonces tenemos al profesor Stuart Holmes el día de hoy. El público puede ir dejando sus preguntas a través de las redes sociales donde están siguiendo esta transmisión. Bien, recordar también, quisiera hacer una mención que la revista oficial de este ciclo de conferencias de la red LAFMAT es el Heat Treatments and Surface Engineering del Taylor and Francis, de la editorial Taylor and Francis. Perfecto. Entonces tenemos profesor Stuart Holmes. Can you start sharing your screen and start your talk?
Okay, Liz, thank you. Okay, apologies. I'm speaking in English today. Sorry, my Spanish is not quality. Thank you, Lewis, and thank you, the committee, for allowing me to speak today. I want to tell you about some work that I've been doing. I'll just change the slide to highlight things. I'm going to tell you about the electronic properties of germanium-tin quantum wells, and really why should we be interested in these materials? Why should we be interested in these devices? It's a collaborative effort. Most of the work I do is a collaborative effort. The electrical transport measurements are made at the London Centre for Nanotechnology, which is a lab in University College London. The devices themselves are fabricated in the University of Cambridge. We have very, very good clean rooms there. We test the devices there, we check them out, and then we measure them in the London Centre for Nanotechnology. The actual materials themselves, the wafers, they are grown at the University of Warwick, which is near a city called Coventry, which is in the West Midlands, near Birmingham, in the United Kingdom. Also, we have access to national facilities in France, where there is high field laboratory. I think a few weeks ago we had a talk from somebody from Grenoble who was in a lab next door to the high field lab. We go there. We have very good funding for this project from the Science and Engineering Research Council. I'd just like to thank my collaborators. We had Yilmaz Gul, who was a PhD student at UCL. We have Maxim Mironov, who grows the materials in Warwick. And we have the PI, Professor Pepper, who's based now at UCL. I'll just go back a few years before I get into the talk. I'll just go back a few years and just explain how we got interested in germanium. I mean, we started with some work that was done at the Cavendish laboratory, and we found that germanium itself was quite interesting from a spintronic point of view. So we applied for a research grant with Warwick University and the University of Southampton, and we got all this funding to study germanium materials. And the more we looked at this material, the more interesting it was. I've just picked one paper here. You might recognise a few names here: Lewis, myself, Professor Barnes, a few other people. Used quite a few papers on this. And then the field went quiet, and then Germanium-Tin came along. So why would you add tin? So I'll explain that. This is the contents of my talk. I'll explain why we would add tin to germanium and what are the advantages of doing that. I'll then tell you about the electrical properties of germanium-tin. We make foaming contacts to them, we cool them down, we apply magnetic fields. What I'll then tell you about is how they go insulated at low temperatures. They show a very strong localization behavior. Then I'll explain their behavior in high magnetic fields, work we did in Grenoble, and then I'll give you an overall. Okay, so I've picked a paper from the literature here. It's a fantastic paper. It's work that's been done on a germanium-tin, a very thin germanium-tin layer. Barrier materials are germanium, so it's a germanium-tin quantum well, germanium barrier material, and they've done some optical measurements. This is a kind of a photoluminescence plot from this structure here. The little disc there is germanium-tin, and the little bit that's been etched away is the germanium layer. The rough area at the bottom is the silicon substrate. We grow these on silicon, but there's a great selectivity in the edge. We can make these nanostructures. And what they found is that the material has some properties of a direct band gap. It means that optical devices, lasers, optical detectors, emitters, all the usual kind of stuff could be made in a silicon-based device if we include tin in there. If we look at the band structure of germanium, so this is now in momentum space. The green is the conduction band at the gamma point, the so-called direct band gap. The black here is the valence band, so this is a whole band. And you can see here this red band, which is another part of the conduction band that's considered minimum, is actually the lowest part of the structure. The lowest energy is in the L band. So this material is indirect. Germanium is indirect. It's not very good for optical devices. However, if we add tin, add a very small amount of tin, what happens here is the gamma level comes down and the L both come down, but the gamma level comes down down faster in composition. The material switches over to a direct band gap. That's why we can see this photoluminescence. Very interesting photoluminescence. The spectrum here is rather complicated because there are all kinds of modes. It's not just a simple issue. Any set of modes. However, once we make this structure with tin, we find that it's very, very difficult to make the structure without introducing strain. You can imagine if you etch away some of the germanium, the material has to be relaxed. But when it's in an epitaxial form, in a wafer, the germanium-tin has a larger lattice constant. We've got to be compressed down. The germanium-tin layer is in compression, and that tends to open up the band gap. But the L band shifts up. So when you grow this material, well, the bulk might be a direct band gap. With the strain, with compressive strain, the gap opens up and becomes indirect. L minimum drops down again. If we were to somehow have a tensile strain, perhaps gaps on silicon. So the silicon has a larger lattice constant. Right on silicon, the crystal would have to be under tension rather than compression. Then the direct band gap reappears again. So that's why germanium-tin is interesting, that it opens up this possibility of direct band gaps in silicon-based structure. The same group, I think different authors, but the same group, they've done some more detailed calculations using density functional theory. So this is a kind of a theoretical picture. This is 5% tin. You can see the L, I've just kind of coloured in the lowest part of the conduction band. The L is the lowest part of the conduction band here. As we put more tin in, this is up to 15%. You can see this forms the lowest part of the conduction band. As we put a bit more tin in, still the lowest part of the conduction band, but we reduce the band gaps. We tune the band gap to tin. We can tune which is the lowest minimum, and we can tune. That's basically the kind of the theoretical aspect. In practice, it's a little more difficult. The reason why it's more difficult is that the tin is such a large atom. Really doesn't like to sit in a germanium lattice. So when you grow this material, tin tends to surface segregate. If you try to incorporate tin into the lattice, and the tin just sits on the surface, it causes problems for growth. So I've picked another paper here, still in the kind of the background of this material system. Casper, I think his first name is Eric. Eric Casper has many papers on this field: silicon, germanium, tin. They found that one of the early growth papers that germanium-tin can be grown epitaxially on a germanium layer on a silicon substrate. So we have a silicon substrate, a germanium buffer layer, which is relaxed, and then a germanium-tin layer, and they can be grown in a coherent epitaxial way. This is an X-ray measurement. So this is the silicon from the substrate. You can see the germanium is shifted here because germanium has a different lattice constant. It's relaxed. Germanium-tin is coherent with the germanium layer, and the way that this was overcome, this problem of epitaxy was overcome, was to use a very low growth temperature. When you grow these materials at lower temperature, incorporate tin into the lattice, but you tend to get other things like impurities, in carbon, oxygen, and like that wouldn't normally get incorporated at temperature. What happens when you try to dope this material? Can you enhance its conductivity, either N-type or P-type? The answer is yes. This is another paper from about 10 years ago. The early work was done about 10 years ago. So this is some work from IMEC in Belgium, kind of a consortium of universities that did this work. You can see here, this is whole concentration caused by doping. So actually boron into the material. Boron acts as a dopant. It also introduces scattering, so the mobility drops. If you were to do a whole measurement of room temperature mobility, this is germanium, the solid black germanium. You can see the mobilities are actually quite high. For room temperature mobility is quite high. What happens when you boron into germanium-tin is the mobility drops, but it's not too bad. Okay, so we can dope this material, we can grow this material. What are its electrical properties like? Is it going to be useful for the electronic industry? That's the question. So we started, the lowest minimum is the L point, but it's not occupied. The is at p-type though. It really matter too much. You can see what's happening in the valence band. This is the chemical potential here. We just have this heavy hole band. The light hole band is split off for two reasons. One is quantum alignment, we made a quantum well. The second reason, that it's strain. So that strain shifts the light hole band away from the head. When we look at what we've grown, we use a technique called SIMS. I think it's secondary ion mass spectroscopy, so it's a good way of measuring what's in your device. But there's a lot of information here. On the y-axis, I'm plotting duration of impurity. On the x-axis, I'm plotting distance from the surface. We can chemically profile, this is standard technique. Chemically profile what we have in the system. So this is where the real surface is. This first line here. This line here is hydrogen. You can see we've got 3 times 10 to the 18 bits of hydrogen in the system. Hydrogen is very good at passivating impurities, so that level of hydrogen is actually quite beneficial. Impurities and causes the mobility to rise. We've got some oxygen in here, got U10 to the 17 of oxygen. We've also got boron. Now we know we've got boron because we intentionally put it in there. So the boron is the doping. You can see it's quite low here and just peaks where we put in the modulation doping. So the boron is actually quite good as modulation doping. It doesn't extend out to well. This region is the quantum well here, and this is the tin composition on the second y-axis on this side. We can measure the tin composition. More importantly, you can see a second tail here on the tin composition, and that's because the tin doesn't get incorporated in the lattice. It likes to surface segregate. So it produces this, let's call it a disordered defect region on the close to the surface, and this disorder is caused by things. Okay, so what happens when we cool this device down? So we make something called a ball bar. We put contacts on there which are platinum. We anneal the platinum into the device. Contacts on. We cool the device down. We saw these very, very clear quantum oscillations due to the mass effect. So this is the y-axis here is resistivity, passing a small current, measuring the voltage drop along the whole bar. We measure that as a function of magnetic field. Blue line is the 2 Kelvin. We have a very nice. This data was taken in the LCN at UCL. Very nice system for doing this. Blue line is at 2 Kelvin. As we heat the device up, you can see two things that happen. First of all, we lose the quantum oscillations. The quantum oscillations are damped. They're thermally damped. The second point is that the resistivity is dropping. We heat the device up. Only heated it up by 3 Kelvin. Huge change in device resistance. So that was something that we got a very, very clear magnetic oscillation. The device itself was very, very temperature sensitive. If we look at the damping of this oscillation, damping of the mass effect, it's given by the term X over shine X, where shine X is hyperbolic side. X is a measure of the thermal damping. So T is temperature, H bar omega C is the cyclotron energy. So 2 pi squared kT is about 20 kT of C. Cyclotron frequency related to mass. How this thermal damping term changes temperature is a good indication of the effective mass, good measure of the effective mass of the carrier. We found that the effective mass is about 0.09 times the electron mass. But it's a very light, it's a heavy hole, but it's a very, very light heavy, which is very, very good for transport. Not anywhere near close to 0.2.3 times the electron mass it might be. So it's a very, very light mass. We also cooled the system down further to investigate what happens at lower temperatures. We have a system called the Triton dilution refrigerator. That goes down to 30 millikelvin. So we start at 700 millikelvin. Data here at 700 millikelvin. Again, we've got this, as we cool down, we've got this very, very strong temperature dependence. We've got this very, very clear Schuldnikov-de-Haas effect. We also see something called the quantum Hall effect. It's all very, very behaved. We also start to see this very, very strong positive magnetic resistance effect coming in, which is another hallmark of localization, resistive behavior. If we look at the oscillations and measure where the oscillations start in the field, we have a condition mu times v equals 1, where mu is the mobility and v is the field. We know in these structures that the quantum mobility is very, very high in these. We can actually see down to filling factors 58 or 58 Landau levels, very, very clear magnetosity difference. If you saw this, you might think that your transport mobility would be in the millions. This is another measure of Schuldnikov-de-Haas effect. If we look at the transport mobility, so that's the zero field resistance combined with the Hall effect. Hall effect gives us about 4 10 to the 11 carriers. We can measure the carrier density from the period of the Schuldnikov-de-Haas effect, and we can measure it from the Hall effect. And in these materials, they agree very, very well. So we've got two different techniques. It tells us that the charge is in the quantum well. There's no charge in the substrate or the buffer layers on the surface, which is contributing a parallel conduction effect. They're very well behaved, two-dimensional Hall gases. If we Fourier transform these oscillations, they are periodic in 1B, get out something called field. That fundamental field is related to carrier density. Interestingly enough, this is a Fourier transform of the data between the two lines here. The peak in the Fourier transform is related to quantum mobility, 37,000. As I said earlier, it's characteristic of the material that might have a transport mobility of 1 million. But in this material, the transport mobility is only 380. Very, very unusual system. As I mentioned in the first slide on the transport, we saw this very, very strong temperature dependence. If we measure the conductivity, so this is conductivity now, how we measure the conductivity, imagine samples resistor, we can pass a current I through the resistor, we can measure the voltage V dropped across the resistor. The resistivity is the voltage divided by the current, and the conductivity is simply the inverse of the resistivity. Very, very simple. Right? Keep the currents low so we don't heat the device, we don't have in here. What we found in the conductivity is we found that it's thermally activated. So what's happening is, this is the valence band here, we've got the Hall energy, so this is positive Hall energies now. So this is where the cursor is the band gap, this is the Hall energy. This is the chemical potential, the dotted line here. And what we're seeing is a thermal excitation from mobility edge. So the carriers have to be excited to this point in the band conduct. So it's a thermally activated process. It's an Arrhenius behavior. The temperature dependence of the conductivity is basically this energy here compared to KT, eta minus W or AT, or we sometimes just think of it in terms of characteristic temperature, zero. And so the conductivity was representative of this mobility transport to a mobility edge. We measured the mobility. The mobility had the same temperature dependence, so it's the mobility that's not an activation of the carrier density. If it was a doped semiconductor, you might say, well, it's just activation of the carrier density, but it's not. It's actually affecting the mobility. They have the same characteristic temperature, fitting the conductance and fitting the mobility of the same temperature dependence. So at this point, we decided to make further devices. We published the data over when we have COVID lockdowns in the UK. We managed to then make some gated devices. So the next part is really to explain to you what we see in the gated devices. First type of device that we tried to make, the so-called backgate device, where we take the wafer and we mechanically thin down the substrate and then attach a titanium gold backgate. So we can use that backgate as a back electrode. We thought we could control the carrier density of quantum well. We thin the substrate down to about 40 microns. It does mean that you've got a rather thick substrate still, but you need quite a lot of voltage here to do anything, change anything. We found using this technique here, we don't actually change the carrier density. This is the carrier density from a Hall effect measurement function or voltage. So we put 40 volts on the device there. Certainly wouldn't be of any use in the electronics industry if you have 40 volts there. What we did find was there was a small change in mobility. But what we thought was happening was we were just changing the scattering. We were just perhaps changing the shape of the quantum well and introducing some wave function. We sorted in the quantum well. We just see a scattering. We didn't see any problem changes in carrier. In that, we had to make an FET device. So the FET device, field effect transistor device, consists of a Hall bar, standard Hall bar where we've etched away. We use standard chemical etching to make the pattern. We put down an ohmic contact, which is made of platinum. Use the ohmic contact here. So this is the source, this is the drain. These are the potential arms where we can measure resistivity along the bar. We can also measure the Hall voltage across the bar. What different here is we've put down an insulator there, aluminium oxide, ALD, by ALD, atomic layer deposition, and put down the top gate on. And if we repeat those Hall measurements, you can see here this is carrier density P. Traditionally we call Holmes P-type. Hall density is P as a function of top gate voltage. Now it's a whole gas, so it responds by depleting out or reducing the carrier density from positive gate voltages. These are 1, 2, 3, 4 devices. They all show roughly the same slope here, changing carrier density and gate voltage. This actually might be useful for a CMOS type device because we're only applying about 1 volt, so the device is depleting by about 1 volt. The slope of this line is the capacitor. Think of it as a parallel plane. That slope is telling you about geometry. What's different with germanium compared to silicon is that germanium doesn't have a very, very nice oxide. The whole electronic industry was built around the silicon dioxide being a nice gate dielectric. Germanium doesn't have that. Germanium oxide, so kind of the natural oxide on the surface, is water soluble. Well, that causes major problems for the electronic industry. However, this thin AL with the thin ALD, we're able to make devices. This is at lower temperatures. You can see the whole density as a function of gate voltage again. We can either go into enhancement mode, so we can apply a negative gate voltage, put in up to something like 6, 10, 11. So the ungated devices, they have about 4, 10 to the 11 carriers. These devices, we can push them up to about 6, 10, 11. Very, very clearly metallic. That region, in a depleted region, they go very, very insulating. We can also measure mobilities as a function of carrier density. So by changing the gate voltage, we change the carrier density. We tend to see two regions in these devices. Region 1 here, where not really much happens to the mobility. It's a constant mobility. Could be related to phonon scattering. We're not exactly sure. But in region 2 here, the mobility is power law. The whole density power is 1. Okay, it's linear. That is very characteristic of impurities in the quantum realm, so-called background impurities. So we know we've got these background impurities in the quantum realm that are causing the limiting mobility. When we cool these devices down in the fridge, it's actually quite dramatic. We measure the conductivity. So this is the conductivity at constant, the left-hand side here. This is the conductivity at constant temperature. This is at 1 millikelvin. As we deplete the device, the conductivity drops. And then at some point we just lose the device. It just goes very, very resistive. The way we measure them becomes a problem. We use small currents. We get things like phase shift in the signal. And what happens as we cool the device down is the conductance drops. Still at low temperatures, we start to see several features. We start to see fluctuation. We start to see the conductance turning round and increasing. Conductance increasing as we reduce the carrier density. So some metallic behavior. But we also see this very, very dramatic change in the device characteristics at around 1.5, 10, 11 carrier density. We can plot this out as a function of carrier density. These are all at constant temperatures. Conductance down, the contacts start to get this information noise. But then at very, very low carriers, we lose the device. It becomes resistive. I've put in a false colour plot here. You probably can't quite see the axis. This is applied magnetic field as a function of gate voltage. You can see several things here. You can see the Landau level structure developing. You can't see that if you close your eyes and look carefully. You can see the Landau level structure here changing. This is a high field. You also see this fluctuation noise here coming in. And although it's noise, it's reproducible noise. If I change the temperature, the same noise feature is still there. Or if I change the field, the same noise feature is there. This is very, very characteristic of a endoscopic device. We tend to get switching, we tend to get some conductance fluctuating. So that's very, very characteristic of these structures. So that was in what I've just described to you there, was in device 1. If we plot now, instead of plotting the conductance hole density with the gate, if we plot the conductance versus 1 over T, fixed carrier density, so going from about 4, 10 to the 11 down to about 0.6, that's where the device goes into resistive. You can see it's thermally activated, follows a 1 over T law, exponential 1 over T law. Interestingly enough, you can see that the intercept comes down. The intercept comes down because of activation. You can imagine that as we lower carrier density, the holes have less material to diffuse through. It's still diffusion, the holes have less material to diffuse through, so the high temperature intercept tends to come down because of this percolation effect. It does actually come down to a constant point, and I'll come on to that in a few slides' time. So it's still this thermal excitation to a mobility edge. It's very, very well described by Arrhenius behaviour. When we looked at a second device number 2, so it's from the same wafer, it has the same structure, it's just a different batch in processing. We were much more careful at monitoring what was going on in the device. So the conductance, this is our device conductance as a gate voltage or area density, comes down, turns round, and then it charges up. Same as we reduce the temperature, we get the same features, we get the drop in conductance, we get the slight turn up, then we get the sudden increase in the activation energy, plus this endoscopic norm. We plot this data out as a function of 1 over t log versus 1 over t. We've got the straight line behaviour, and then we've got this sudden increase at around 1.5 or 6 10 to the 11. We plot out the parameters from that fit. What I'm plotting here is for each data set, fixed carrier density, I'm plotting sigma function. I'm plotting the Arrhenius behaviour for activity, and the 2 parameters that come out of the fit, those straight line fits, are sigma naught, that's the high temperature intercept, and T naught, that is a measure of the gap between the chemical potential and the mobility edge. And if we plot those parameters out, I've plotted sigma naught out against T0. There are a lot of measurements here, many, 3, 4 sets, 5, 6 sets of data on different devices, different cool downs, and we see a fairly universal behaviour. I'm pretty convinced this is a universal behaviour. Sigma 0 comes down, it comes down to 0.76 E squared over H. This is very, very close to the Mott minimum metallic conductivity level predicted by Mott. Second device comes down, doesn't quite reach that minimum metallic state, but then goes very, very resistant. So device 2 goes very, very resistant. At this point, device 1 comes down to this minimum metallic state and then goes very resistant. So really what's going on, if you plot out now T0, that's T0 from the fit, from the temperature dependence and conductivity. If we plot out T0 as a function of carrier density, high carrier density, it's very, very metallic. It does show this thermal activation to a mobility edge. As we change the position of the chemical potential, that energy increases, and then at some point that energy really increases very rapidly. It's almost like a transition. I wouldn't say it's a metal insulated transition. It's very, very close to a metal insulated. It's very, very high, a very, very rapid change of activation energy. And there's 2 things that come out of this. It must mean that in this region here, around 1.6 10 11, we have a gap in the density of states. So this inverse gradient is really a measure of the density of states. So at high carrier densities, we have a high density of states here, and then the density is almost a gap in the density of states. The other point is what we don't see is any other type of conductance behaviour. If you look in the literature, you might say, oh, well, it just goes over to being hopping. So we get this we see this, variable range hopping. It's variable range hopping, but it isn't. With variable range hopping, conductivity will be given by an Arrhenius behaviour, but with an extra power P in there. And for variable either a half or a third, depending on the type of variable range hopping. If it was MOT variable range hopping, it would be a third power. If it was Eflin-Mikulowski, it would be a power of a half. Don't seem to get this part. This is the actual mechanism. When you have variable range hopping, you have the system is localized. You have, in our case, we have a charge that is quantum well that sees the disorder caused by the tin segregation. And what happens is the transport is not by diffusion, but by hopping. An occupied state here, just with low mechanical potential, finds a vacant state, beta, alpha to beta, and hops. The device hop through the device, and it's an activated, thermally activated process. This hop energy here, this difference in energy in the states, is not a fixed quantity. That gives this additional power lead. We don't seem to see that. So I'll just quickly mention what we did in Grenoble. We applied even higher magnetic fields. Grenoble, the lab in Grenoble is part of the CNRS facility in France, the National Scientific Lab for Research in France. It's a very, very nice facility. We can get 36 Tesla, huge magnetic fields. You sweep up to 36 Tesla minutes. It's funded. We get the funding from our own physical society, our own research council that we take to Grenoble. So this is what happens at high field. This is device resistivity now as a function of magnetic field. This is up to 25 Tesla. At higher fields, the device really does go resistive. This is on the left-hand side here. We've got device resistivity. You see it's going up to 10 mega ohms. That's a 4-contact resistance measurement. 4-contact resistance. Very difficult to do. It's also in a fridge. We can go down to 100 millikelvin. So it's a very sophisticated equipment. The device measurements themselves are a little bit awkward. If we plot the resistivity out here on a log scale, so it's log of resistivity now, you can see the underlying Shubnikov-Haas effect. It's low, really at low fields, the device resistivity increasing. You can see the carrier density is not changing, so the periodicity of the Shubnikov-Haas effect is not changing. This is filling factor 1 here. Although we're up to of the order of 10 to the 6 ohms per square, we're still not losing carriers. We have as many carriers as we start. So this localization effect is not losing carriers. If we plot the numbers out, so I'm plotting resistivity now, field as a function of temperature. So this is as a function of inverse temperature. So this is inverse temperature. The resistivity fits here to the in a similar fashion to the activated conductivity. Well, the resistivity has the same behavior. We get it to 0. You can see T0, that's the gradient of this line, slightly increases as we go up. Also, you can see that the intercept comes down to 1 over sigma 0. That's this watt minimum metallic conductivity. So it starts at this minimum metallic, which is a concept. It's a concept. Starts at this minimum metallic conductivity. When you apply a magnetic field, the current is applied to the edge of the device, the intercept, 0 temperature or the high temperature intercept. Still don't see any variable range hopping. So the black triangle here is at 0 Tesla. There is absolutely no change when we're at filling factor 1. So filling factor 1 is a single spin polarized Landau level. We have the same behavior. There's no change to variable range hopping. There's no in fact we can go up to half a Landau level, half we just got active no variable range So just to summarise, I'm nearly finished now. This is a summary of what we observe in this material. As I said, I put the title here, Nature Abhors the Metallic State. Now that may or may not be true. We've got a metallic light system. So this is carrier density or hole density. It's metallic like, this is temperature here. On the other side, we've got an insulator. And we have several studiable features between the two. Is have a conductance which is not zero, but it's got a thermal activation to another edge. Change in the carrier density with temperature is zero. We don't lose carriers. There's no magnetic freeze out. Carrier density is set by the doping level, what they call gate voltage. We have this very, very clear minimum metallic conductivity given by the very, very close to the Mach value. So it behaves in a sense like a textbook ordered system. In the insulating phase, the conductivity goes to zero. The conductivity becomes so small, it's very, very difficult to measure. But we also see features like the conductance, slightly on the metallic side, loses its temperature dependence. Okay, it's on the metallic side. We also have this turn up in the conductance. There's obviously something else going on there that we don't. So in summary, these germanium-tin modulation dot structures, they have a high quantum mobility, 36,000. That would be characteristic of the type germanium that perhaps had a transport mobility of 1 million. This system, we've got this order effect, transport mobility is 180 centimeters. So that is high enough to give us quantum oscillations on metallic type. We get the effective mass for free in this material. This measurement gives us an estimation of the effective mass from the thermal damping of the mass effect. It's about 0.09, so it's nice and light. We see this localized behavior in the conductance, and we don't see variable range hop. It could be that if we were to measure the device at lower carrier densities, controllably at lower carrier densities or at lower temperatures, we might see a variable hop, variable range hop. And just to mention what we plan in the future with these materials is controlled disorder. If we're in control of the disorder, let's make use of that. Let's fabricate freestanding structures to take away the thermal bath. So this is an SEM image from my co-workers in Cambridge. She's produced this structure. This is actually a selectively etched freestanding hole bar. So this is part of the hole bar that I showed you before. It's actually in indium gallium arsenide, not in germanium or germanium-tin. But we could use the same processing. You can see actually the very faint light line there, and that is an indium gallium arsenide quantum well. So we can make freestanding quantum wells. And the interesting part of this device is that it's not connected, or it's very, very weakly connected to the thermal bar. But it's not connected to the substrate. There's an air gap here, and it's only weakly connected to the contact. Could be a thermal bar. And what we would hope to do is to shift from a diffusive to the conductivity, which is basically the transport mechanisms that I've showed you, into this phonon-assisted hopping regime, which we don't see in the germanium-tin. What we would like to do is to study the effects of many-body localization, where we've taken away the thermal link to a reservoir, and the only noise we've got in the system is a Nyquist noise, so it's kind of an intrinsic electron or hole noise in the system that perhaps drives this activity. And then in such systems, we could study non-ergodic behavior. crystallization, so that really temperature, in a sense, has no meaning because heat can't travel through the system, charge can't travel through the system, but also heat can't travel. That's what we would hope. Thank you.
Muchas gracias, Stuart Holmes. Thank you very much, Stuart Holmes, for your nice talk. Now it is time for the questions from the panelists. Ahora vamos a pasar con las preguntas de los panelistas. En primer lugar, representante del CIPESTAC de México, el profesor Arturo Martínez. Arturo Martínez.
Acá estoy. Gracias, Luis. Stuart, I saw in your slide 23 two different graphs.
Yeah.
This one. What is the difference? It's only the logarithmic scale.
Yeah, so the left-hand side is a linear resistivity. The right-hand side is a logarithmic scale, just to show the data that's all down here. There's no reason for it to be on a logarithmic scale. It's just easier to see the oscillatories here.
Okay.
Yeah, so it's still a Shubnikov-de-Haas effect, still this magneto-oscillation effect. It's just easier to see here. Interestingly enough, the oscillation is not damped, so the quantum mobility, the quality of the oscillation is not thermally damped in the way that the transport is temporary.
Okay. Very nice talk.
Thank you.
Thank you.
Okay. Muchas gracias. Thank you very much, profesor Arturo Martínez. Tu micrófono, Arturo. Okay. Thank you very much. Gracias, Arturo Martínez. Pasamos ahora con las preguntas del representante de la Universidad Federal de Pernambuco, en Brasil, el profesor Albino Aguiar. Albino.
Hello. Can you hear me?
Yeah.
Yeah.
Yeah. Stuart, congratulations for the very nice detailed talk. I'm not used to work in this area, but I have one question for you. If I understood correctly, the substrate was silicon, yeah?
Yeah.
What happened if you use graphene as a substrate? Do you have any?
But if we use graphene as a substrate, that's a good question. It would be possible to use graphene as a substrate because I think the growth temperature is quite low. It might be good for studying transport in graphene, or having the graphene as an active part of the device. You could perhaps consider a double system where you have a conducting graphene layer and a conducting germanium-tin layer. That might be an interesting device to understand. You could also use a graphene layer, possibly as a gate, to apply a voltage, change the carrier density in the quantum well. I think processing-wise, having graphene there may help. These layers are difficult to process. It could open up possible double layer systems, double quantum well systems. It may be that there is some fundamental difference. Like graphene, like germanium-tin doesn't grow on graphene, for example. We know it grows on silicon. There's good publication showing growth on silicon.
I have no idea, Stuart. I agree with you. If it's possible, you can play with graphene from insulator or semiconductor chemicals. Maybe this can give you more.
Yeah.
More
it's interesting also because tin, if you were to grow tin is predicted to be a topological insulator. So it has some, in a sense, it's similar to graphene. It's similar to graphene. It's got semi-metallic like with some linear properties to the band structure. So it does look a little bit like graphene. You just have tin.
Okay.
We could possibly grow tin, metallic tin. Would have some similar properties.
Yes. Okay, thank you very much. Congratulations.
Muchas gracias, profesor Albino Aguiar, de la Universidad Federal de Pernambuco. Ahora pasamos al representante de la Universidad de San Sebastián, Puerto Montt, Chile, el profesor Felipe Mundaca. Felipe.
Sí, gracias.
Tu cámara,
Thanks
por favor.
¿Sí se escucha, no?
Sí, tu cámara puedes activar, por favor.
Okay, thanks for your presentation, lecture. I have a question about your electric mixture. How in that graph, how you measure that resistivity versus magnetic field? What is your method to measure?
So I'll just quickly show you. So if you look at the structure here, what we do is we pass a current down the Hall bar, a small current, usually 1 nanoamp, and we measure the voltage drop along the Hall bar on other contacts, and that gives us a resistivity. And then we apply a perpendicular magnetic field. The field is perpendicular to the device.
Is Hall
answer
effect or
yeah, so we can measure the Hall effect. The Hall effect would be this contact, so across the Hall, and the resistivity, our RXX, would be along the Hall bar. I didn't show any Hall effect data from Grenoble, but we have the data also. It's a standard resistivity measurement.
Okay, yes. Okay, thanks.
Ok, gracias, Felipe Mundaca, de la Universidad de San Sebastián de Puerto Montt, Chile. Bien, ahora desde México pasamos con el profesor Francisco Paraguay. Francisco.
Hi, good morning, everybody. Well, thank you for your nice talk, Stuart. This is interesting studying the multi-layer systems. I know about this type of materials. You are growing by molecular beam epitaxy, I think.
Yeah.
And the property is interesting. The property is interesting of this compose of different layer.
Yeah.
What about the microstructure? When you are studying the microstructure, what about this one? It's important. It has a strong influence or not? Please
Yes. So
talk about a little bit about the microstructure of these materials. Of
Yeah,
this layer.
So our collaborators that grow the wafers, they do X-ray on the system, and they know two things. They know that the layer is coherent with the barrier material. Barrier is germanium. Germanium-Tin grows coherently. They also know that it's strained, so they know that it's strained, but it's in compressive strain. They also know from the SIMS measurements that the tin also surface segregates, so we get this second peak here in the tin. Tin likes to stay on the surface as you grow, it stays on the surface. So they have to use low temperature growth to incorporate the tin. I think the tin is a very large atom. But I think there should be some good structural studies on this material system to understand the epitaxy in more detail. I think that should happen. Good question. We've gone straight into making devices without really knowing the structure properly.
Yeah. It's interesting in this case is the elemental composition of the different layers. But I was thinking in the structure, what kind of structure is cubic, hexagonal, or
it's got the same.
I don't know.
It's cubic. Yeah.
Oh yeah.
It's a cubic form of the crystal.
Okay. Yeah, this is interesting. The diffusion of the germanium, the tin diffusion in the other layer, and this has a influence in the property something.
Well,
this one.
Yes. So we thought it might form a double quantum well, so two quantum wells together with different tin composition. But now we think that the second tin layer just adds a disorder, a kind of a disordered region. It doesn't actually form a quantum well, it just adds disorder, like scattering sectors, things like that. That's why we think we see the localization effects, these scatterings. That's why the layers go very resisted.
Yeah, this is interesting because there is a other quantum well close.
Yeah, exactly.
Okay, but it's interesting. Okay,
Thank you.
Nice work, nice talk. Thank you.
Gracias, muy amable, Francisco Paraguay, México. Bien, well, I think that some help for Francisco Paraguay is also the first article you show. Can you show maybe, because there in the first article we show.
This one, Lewis?
Yes, in that article,
yeah,
we have published it some years ago with Professor Ángel Bustamante from the University of San Marcos, Peru, with Adrian Ionescu from Cambridge, people from also Cambridge who are now in France, Switzerland, and so on. People, some friends, and there, for Francisco Paraguay, we started with an amorphous germanium, and after that we have improved the crystallization. From amorphous, we made the germanium crystalline and polycrystal, unfortunately, not monocrystal. Then it unfortunately also oxidizes and also diffuses. There is a diffusion germanium into silicon, and there is a reaction as well between germanium and the germanium oxide. There is a lot of it's quite tricky to work with germanium in that case, the crystallization. However, in order to avoid all these problems, Stuart Holmes has grown this by MBE, right?
That's
MBE,
right, yeah.
With molecular beam epitaxy, grow with big chambers and so on. But Francisco Paraguay, you are invited to read this article, could give you more information about us. Entonces, este artículo puede dar mayor información. Te podemos pasar este artículo que hemos publicado años anteriores con Stuart Holmes. Su nombre también está ahí. Ángel Bustamante está también de San Marcos. los amigos que estamos ahí colaborando, ¿no? En fin, te pasamos este artículo luego para ahí quizás te pueda ayudar por mejor. Bien, entonces damos la bienvenida también al profesor desde Ecuador, al profesor Juan Primera. Juan, ¿tienes alguna pregunta desde Ecuador?
Buenos días con todo. Lamentablemente, y pido disculpas, me he incorporado un poco tarde a la conferencia y mal podría yo estar preguntando. Muchísimas gracias.
Ok, no te preocupes, Juan Primera. Bien, pasamos a las preguntas del público. James Godoy, ¿tenemos preguntas del público en la Universidad de San Marcos de Perú o tenemos preguntas del público peruano? James.
Profesor Luis, gracias. No hay preguntas del público. Solo agradecimiento por la excelente exposición del profesor Holmes. Gracias.
Bien, Ximena Velázquez, ¿hay preguntas de la Universidad de Colombia, del público colombiano?
No, en este momento no hay preguntas. Nosotros solamente podemos decir muchas gracias por la conferencia tan interesante que nos acaba de brindar el profesor Stuart Holmes.
Stuart, they are saying thank you for all your talks and so on, and very interesting and so on. Well, del público brasileiro, Albino, ¿hay alguna pregunta del público brasileiro?
Luis, no, there is no question here.
Okay.
People are celebrating St. John.
Okay. Okay. Well, thank you very much, Stuart Holmes. Gracias, muchas gracias, Stuart Holmes. Maybe you have some words to say goodbye or so. Algunas palabras.
I would like to say thank you